All right, very good. It's a pleasure to have you from the Department of Statistics, University of Warwick, to present work on differential privacy in distributed learning, and in connection with something that I'm particularly interested in, also federated learning.
Right. Thanks very much for the invitation, and thanks very much for the introduction. So yes, I'm going to talk about differential privacy in distributed learning, and a slightly different flavor from all the previous talks. So when you have this distributed data sets, I think all the previous talks I'm mentioning, the focus is how you can utilize different data sets to have a better understanding of a certain target set, so on and so forth. I will touch a little bit on that in my talk, but the main focus of the talk is really how to preserve privacy, and with different notions of privacy, what kind of the cost of privacy we are expecting in the next sense. Right, so yeah, that's basically what we're going to have, and we'll just a very standard notation. We talk about the privacy mechanism. What we are really talking about is a conditional distribution, and conditional distribution is conditional on the raw data you are inputting. And let's start with the differential privacy, and this is a very standard notation definition here. The differential privacy definition is defined on how much distribution can change if the input is changed. And this is measured by the ratio of the distributions and up to the e to the alpha. And throughout this talk, I'm going to use alpha. Well, I know different epsilon delta, alpha, beta, whatever. But for this talk per se, I'm going to stick with alpha as the privacy budget. And again, I know, well, so for instance, I think, yeah, Pauline Baroon and I keep. Well, I have a very nice papers, and a bunch of we have very nice papers talking about when the epsilon in the low privacy regime, things are behaving differently in some statistical problems. But for this talk per se, I'm going to focus on the high privacy regime, which is and right, let's start with this is a central differential privacy, and the definition is x and x prime. If we are talking about the sample size n, and the neighboring pair x and x prime, we're considering at most one is flipped, one is changed. Right, so this is a central differential privacy. So these are all very standard, but I highlighted some rates here because throughout this talk it's really the only thing is about the rates. So I'm come back again to the rates later. So I just want to highlight the rate. Let's start a very, very simple case. If we're just want to say we want to estimate a mean of a distribution, and we know this distribution is supported down 0, 1. It's a simple supposable situation we're talking about. And if we are using the central differential privacy, an optimal mechanism would be you directly add Laplace noise to the sample mean, and the scale of Laplace noise is 1 over n alpha. And therefore the result is the added noise due to the privacy, the variance is of all the 1 over n square alpha square, okay? Right, so that is about the central differential privacy when we do assume there's a central data curator have access to all the n sample size raw data. Whereas if we move to a stronger notion of differential privacy, which is the local differential privacy, that is that we don't assume the existence of such data, central data curator, and we have to perturb the data individually. So in this case, again, back to this simple supposable problem, the univariate mean estimation problem. If we want to do the local differential privacy, then the added noise. Again, this is the minimax optimal rate, and this will be of all the 1 over n alpha square. So let me just pause here. The central differential privacy, the relationship between the sample size and the budget is n square alpha square, sample size square, budget square. Whereas for the local differential privacy is n alpha square. It's a sample square budget, sample size budget square. Okay. So right, of course, then we said the local differential privacy is much more stringent, and we see that from the rate. Okay. Right, just some remarks, disclaimers, and there are lots of details I won't be able to go through, but just some disclaimer here. I'm not really going to talk too much about the interactive, non-interactive, unless it's become very necessary in 1 or 2 slides. So, and then I'm not going to talk too much about the pure and approximate DP. When it's necessary, I will make a clarification, but I don't want to put too much emphasis on that. But I do want to emphasize here is on the previous slide, we compare the rate between CDP and LDP. And the similarity between these two in the previous slide is we assume one user has 1 unit of data, right? And then we see that, okay, if we have a weaker notion of the differential privacy, which is a CDP, which we assume someone do have access to all the raw data, then we will have a better statistical accuracy. But then if you want to have a stronger notion of a differential privacy, then you have a much worse statistical accuracy. And so can we have something between as well? This is one motivation for us to study this distributed learning, because if we can assume that one user do possess multiple units of data, let's say in a repeated measurement setting, and then probably even if we want to do the local differential privacy, then we can let this user to do something for the repeated measurements they already have before output a private thing, right? So this is one motivation we're studying this distributed learning, but of course we can think this is you have different servers, we have different data sets, and then something can be done within these data sets, but between these data sets, only private information can be communicated. So this is another motivation. And then the connection to the domain adaptation, to the transfer learning, we can also have heterogeneity across different data sets. Distributions can be different, and the privacy concerns can be different. Even if you use the same privacy notion, and the privacy budget can be different. So basically, that's what I'm trying to cover in this talk.
Achieve local differential privacy if one of the agents have very few data. Right? Then local differential privacy is expensive in terms of the variance.
Yes, you can say that. Yeah. We will see the rates in terms of how many, in terms of how many copies of data one user have. So we'll see that one goes into the rates to expand. Yeah. Good. Thanks. I'm just going to proceed. Right. Okay. So this is just some very simple illustration of what I was trying to say. Like we have n servers, we have n users, we have n data sets, whatever terminology you want to use, and only private information can be communicated across these n servers / users. And within this data set, within this user, within this server, we can impose different sort of privacy notion, depends on what your concern is. You can be local differential privacy, can be central differential privacy, or it can be a mixture of both. And our final goal is to understand this distribution. So I'm going to focus on the first bullet point today, but I'm just going to very, very briefly touch the second and third bullet point. So if we think, okay, I call this is a local differential privacy within each server, but I think the terminology we should really use is the user level. I will come back to the more rigorous mathematical definition later, but let's just like a hand waving think, or at a high level think, intuitive think within each server. If you impose this LDP, and this is something we're going to call as a user level, and this is the focus of this talk today. And if you think within this server, this is central DP, and across the servers there are local DP, and well, I think different people call it differently. Some people call federated DP or whatever, and that's the second bullet point. And if you have a mixed structure within, and that's the third bullet point. Right. So why do we care about that? I said that if you want to say there's only one word to summarize my talk today, it will be race. So I'm just terrifying, intimating you with all different race. But the previous few slides I said with the central DP, right? The sample size squared, budget square. Local DP, the sample size budget square. So as you can see in this sample, in this table, what we are trying to say is you have n servers. So at the server level, this is a local DP. So with n, it's local. And within each server, there are T units of data. And then for different type of differential privacy, we see right of no privacy, that is what it is. And with the central level, so for instance, it's both n, okay, so the central user level. So the central item level, this both n and t is squared, and the user level, as I said, you can think user level as LDP, local differential privacy. I will come back to the mathematical later, but it's n squared t, and then there's the main takeaway message for this talk, or the punchline for this talk, is about this local user level. So local user level, when this t, let's back to the question earlier, when this t is small, well, I will define what I mean by small for different problems later. When you don't have, when each user doesn't really have many data, and in this case, this user level and item level, so the so-called item level, okay, there's so many terminology, so many jargons, I don't really like that, but just bear with me then. So the so-called item level, in this case, will be you impose LDP for each of n multiplied by t data points. Okay, so that is the local item level. And the so-called local user level is you apply the LDP for every t unit. And yeah, please. Yeah.
The user has very small data. The cost of local DP for this user will be high, but also I can kind of ignore this user because all the data is the same and he contributes only a little to the pool of the data.
Yeah, so that's probably it's corresponding to when you do have small t, when you don't really have many data points, then this is the same as the item level thing. It's not, you can't really improve as you can't really by doing something with within your t data points in order to improve the rates. Yeah, so far let's just assume everyone has a t. Everyone has t. Yeah, as everyone has t. Yeah. No. Yeah, we didn't really do that. So
the results in the, I guess those that you're calling central user level, or I don't know, those can be generalized to the distributions not being the same or being close to each other. But in any case, are you going to be speaking about what happens to each one of these the distributions are different, or?
I'm only going to talk about that.
Okay.
Only a little bit. So that's not really the main. But I'm happy to talk about it more later. So yes, indeed, so far right. There are the caveats for that. So when I said we started working on this one motivation is we want to do a little bit more if one has more than one copy of data. But then again, what we are also thinking is if you do have repeated measurements, it's a temporal dependence, it must become a thing. But well, I have to confess that for the results we are showing here, we're assuming IID for now. So yeah, it's the temporal dependence is definitely a lot of future work, but for now these are independent. Right. So I think I will very briefly talk about two extensions. So these two extensions is with respect to the illustration I had previously. So one extension is within each server. If you do have some further hierarchy within each server, what can you do? And another is across, which I'm very briefly touching this point, across different data sets, and it have some heterogeneity, and how would the heterogeneity come into the minimax rates? Okay. So as about the first one, the first one, okay, this is the example we worked on. So you can think all these green boxes are the different servers, okay? So across the green boxes, only private things can be transmitted. So at the green level, it's local DP. And within each green box, there are multiple orange bars. And all this within the green box, and this central DP among the orange bars. But for each orange bar, what we actually worked on is the functional data is a sparsely, it's a discretized observed functional data. So each function you observe like m different points. Then within this m, this is a local DP again. This is a user DP again, user level DP again. So there are like three different levels of DP. Right, and then it's N, T, and M, right? So well, ignore all the words here. I just want you to, and as well, because it's a functional data, so you have a parametric rate, non-parametric rate, and the private rate, non-private rate. I don't really want to talk about details of that. I just highlighted different colors. Again, this is back to what I said previously. With the central DP, it's the sample size squared, the budget square. With the local DP, the sample size, budget square. So at the green level, this is a local, and the orange level, this is the central, and the blue level, this is a local again. So yeah, we do it for this hierarchy, and we see this sort of a structure again. So this is one extension I want to say, that when you have this distributed learning and you have further hierarchy structure within each server and with different notions of privacy, how different rates coming together. Another extension, well, this is the thing everyone's asking is like if we have some heterogeneity and how this is coming to play. And this is quite standard, the min-max rates for the transfer learning type problem. The first line, this is basically to say the final min-max rate is the minimum between only using target and you use others. And if the target only rate, this is a private and non-private rate. And the transfer learning rate, so it comes three different parts. It's basically the source target difference. And for different problem, you have a different way to measure the difference. And the non-private and the federated DP rate. And this federated DP rate is basically the thing we've seen in the big table earlier. So yeah, this is with the heterogeneity, right? So these are the two extensions I wanted to say. But what I really want to say is the user level DP. This is to say at the different servers, within different servers, we are considering a local DP. So I'm going to jump into the thing I really want to talk about. Any quick questions? Right, so this is a user level DP, and again, then just see this the illustration again. So you have n servers, and across servers only local, it's local DP, and within server we assume each server has t units of data. We assume they have the same number of data, and then it's the user level. It's basically a local level within each server, and there are multiple. Okay, good, because something's true.
Yeah, that comes and goes. Don't worry about it.
Okay, right, thanks. And then there are these orange arrows here. So basically, this tells us we are using an interactive mechanism, but I don't really want to emphasize that. So that is the framework we are talking about. And the rest of the talk, it seems I've already used the half of time, and it's the first time you see the outline. So this is the outline for the rest of the talk. So first I'm going to give the minimax framework, and then I'm going to show you some completely useless thing in practice, which is the infinite T scenario. It's completely useless in practice, but I find it very interesting, and it's guiding us for some final rates for the fixed finite T scenario. And I'm going to focus on, for the less useless situation, I'm going to focus on the sparse high dimensional mean estimation. The reason we are focusing on this is for people who know a bit about the LDP, you probably know that the LDP is a very stringent notion, and even if you know it's a one sparse scenario, you can't really work on it. You can't work on this, is you can't get the sparse rate out. But using the user level DP, we are going to show that we do allow the dimension to go exponential as the sample size. So every user has multiple data does help in some situation. Right, so the minimax framework, and this is the definition for the user level DP, and this is what I said. So basically the user level DP is, right, so I have T copies of data, and by imposing LDP on me, you do allow the whole T dimension data to flip, not just like one of the T's, the whole T dimensional data to flip. So this is from the LDP. So this is from the DP notion. While as the difference between this notion, if you are going to learn a T-dimensional vector, is my statistical learning task is not a T-dimensional object. My statistical learning task is still like one, it's the marginal of every of it. So this is a difference from I'm learning a T-dimensional space, but then you do allow the whole T thing to flip. So this is the difference here, and we are considering this minimax risk here. Should I just, if I stop my Wi-Fi, would it stop it to jump? Okay. Right.
You just can go back this. So did you explain the P and Q here in this in the last definition? I don't think you.
Right, I didn't think. Oh, right, sorry, I do need to explain that because everyone is using P and Q so for source and target. I'm not using P and Q for source and target. P is a distribution for the raw data, and the Q is the privacy mechanism. Okay, so this is not source and target. Yeah, right, exactly. Yeah, thanks very much. Right, so that is the minimax framework, and the motivating example is, okay, so first of all, let's again come back to this simplest situation. We are doing the univariate mean estimation problem, and in this user level LDP minimax rate, and we are considering the squared loss. Okay, if you have n users, each user has T copies of data with alpha privacy budget, the minimax risk is lower bounded by whatever thing written there. It's 1 over NT alpha squared. Okay, so this actually coincides with the item level thing. Then the question is, if you let T diverge, if everyone starts to get more and more data, then will this goes to 0? Well, the answer is no, otherwise I wouldn't ask. And intuitively, the answer is no, is because, okay, so this is basically what we have already shown is when you do have infinite, when T is infinite, okay, I'm going to explain what is this infinite risk is. So when T is infinite, the rate is exponential with respect to n. Okay, n is the number of users. T disappear, T is infinity in this case. So the limit of this guy when T goes to infinity is not 0, it's an exponential thing. It's an exponentially decaying thing. And what is this thing? So we need a mathematical definition for that because we can't just say T goes to infinity. So when T is infinity, what does it mean? That means every user knows the distribution so well. It's not 10 or 5? 9. 9, okay.
10, but it's 9.
Okay, thanks. Well, I think there are 3 types of mathematicians. One can count, one can't count. Right. So what is this definition, right? When I have like infinite copy of data, what does it mean? That means I know the distributions completely. So that is what is this, you replace this capital T by this infinite sign is. And what does that mean? That means as if it equals, I only have one copy of data, but that copy of the data is a Dirac measure on the parameter I exactly want to know. So I exactly know that thing. So when I have infinite data coming from a distribution, it's equivalent to I have one copy of data is a Dirac measure just on the parameter I want to know. So for this, in this case, the sample space is actually a parameter space because you know exactly what your parameter is. Right. So this is our definition. This is a completely like a practically useless case because that's not the situation, but that will guide us through the transition between the so-called small t and the large t. Okay, so this is a general result. And these are n of delta. That's the delta covering number of the metric space. Again, that's what I was trying to say here. In this case, for this infinite t case, the sample space is actually your parameter space. Okay, so what does this? A few remarks about that. The first remark is well, this is the rate. This is the lower bound for the infinite t case, but this lower bound also serves as a lower bound for the minimax rate for any fixed t. Okay. So this is the first remark. And the second remark is we show, well, of course, just from the look, the lower and the upper bounds, they look so different, but well, there's a way to match the upper and the lower bound by choosing delta properly. Problem dependent, but we do assume this is a compact space.
So that's it's a metric space and compact, and that's the
yeah. So from the look of the lower bound, you can guess how we prove this. This is basically just using Fanel's inequality, and because this is a private data, and we need to upper bound the KL divergence it's just to upper bound the private KL divergence, and it's very easy to get a lower bound. And for the upper bound, it's also very easy to get an upper bound. We actually use a non-iterative mechanism. So the idea is you first get the delta covering, and then you make the delta covering non-overlapping, and then you basically make it a long vector. And because every single user knows exactly where the true distribution is, and then it's a long vector with a one and only one entry, and everything else is zero. And then you just use randomized response to perturb it, and you do a majority vote. Yeah, this is still t is infinity, exactly. So this is a useless thing. We just want to get the rate, right? So this is a very simple example, and as you can from this mechanism, you can guess which where all these terms are from. Given that I only have less than 9 minutes, I'm just going to skip that. So we show for different problems. Well, yeah, so the first two columns, these are the parametric rates. As you can see from the finite t to infinite t case, it's coming with respect to n, it's from the polynomial to exponential. And for the last column, this is a non-parametric case, the exponent changes, right? So this is, again, this is infinite t case, this is infinite t case. This is useless, but this useless thing guides us to do some less useless thing. So this is the high-dimensional sparse mean estimation problem. And again, this is a very strong assumption to start with. We assume the support is on the L infinity unit ball, and the mean is sparse. Mean is S sparse, and we are interested to estimate this mean. As I said, this is 1D is large. This is an infeasible problem under the LDP. You cannot get a consistent estimate when D is larger than n alpha squared. But what we are going to show is it's a very messy theorem statement. I'm going to explain them later. So basically, we are going to show for finite t, you can actually get the sparsity out. So if you look at the upper bound, we do see S. So for instance, this term here, this is without D. Okay, D is only in the log factor. Let's forget about log factor for a second. Right, so how do we understand all these rates? Well, I guess you can just trust me for now. You do some simple algebra, you could actually see under some mild, it's not a whole regime. You do need some mild conditions. So once you get some mild condition, you can actually see for this, in this case, the rate is S over T, is these three different terms take maximum. So the implication is when your T is large enough, three minutes. Okay, I can count this time. Good, thanks. Right. So this is the rate. Right. Given that I only have 3 minutes, I will just very briefly say about this upper bound, about these slides. So the lower bound is, well, you can see the lower bound has two parts, and the exponential term, as I said previously, for any fixed finite t, the infinite t lower bound serves as lower bound for this case. So we do have an exponential term in the lower bound. And for the first term, you see S multiplied by this one. You can guess this is basically using the Oswald's method, and you have an upper bound on the private TV distance. So that's how we get the lower bound. As for the upper bound, it's a minimum of 2 terms. So basically, we need to choose between 2 different methods. Depends on if your T is large enough. So when you do have a large T, when everyone has enough data sets, when everyone has enough data points, what you can do is you let every single user to vote which coordinates should be non-zero. So you use half of the users to determine which of the coordinates are non-zero. So the top S coordinates. And then you use the rest half of the user only to estimate the S dimensional thing. So that is why for the first, the rate is S over T. Okay, that's rate is from. However, when T is not large enough, when this mechanism is not guaranteed to be good, you cannot do that. Then what we do is a simple thing is everyone estimate, we use half of data to estimate this D-dimensional thing, but then we just truncate this D-dimensional thing to get the top one. So that's why you actually see this, the second rate is SD over NT alpha squared. So yeah, so hopefully, okay, I'm just going to jump through all this, and hopefully I'm just trying to sell you this idea that there is something it's impossible. So there is something this is impossible when you are considering the item level LDP, but user level having more data can actually help you. And there exists this transition boundary for small t and large t for different problems. So yeah, I'm happy to talk more, but I guess I will stop here. Thanks.
Okay. Any question, summary?
Something you said earlier, but I didn't fully get it. So you were saying that it's something to do with sparsity, and that in a particular situation you could not get that type of rates, but here all of a sudden in the federated situation you could. So can you repeat that? In what situation could you not get
So if you know this is a one sparse high dimensional d-dimensional mean estimation problem with sample size n, and if you want to use this alpha LDP, and the min-max rate is d over n alpha square, even if you know s equals 1. So when d is say larger than n alpha square, then this is not consistent. So that is what I meant.
Okay, so however, here you're getting, in the case where t is large, you're getting the s over n.
S over t.
S over t, sorry,
Yeah.
yeah. For me, n is sample size, but you have reversed it.
Yeah, right, yeah. Yeah.
So S over T, you're getting the S over T. And can you maybe comment quickly on where that's coming from? I know that's what the whole talk was about, but.
We don't have time.
Okay,
We're not
fine,
the
yeah. I can ask you offline also.
Right. So I think I can explain this. Well, if you think this is a central DP, well, central DP is someone do have access to all the raw data, and then in that case, the rate will be SD over n, whatever sample size. Right. So it's because someone can use all the data to do something before output a private to perturb a thing. Right. So for the LDP, no one can really have all the data. Everyone only has one unit data, and when you impose this LDP, you have to perturb a d-dimensional thing. Even if you know it's a sum coordinate, it's only one. But with this multiple data, then you can use this t data points to help you determine, to nail down to. So when t is large enough, you can know it with a good probability that this is for sure.
Is there any other question? All right, so then let's thank the speaker. Thank you.